Hey everybody, and welcome back to another week of Fastbook. So this week is week 5, and I'm excited. So last week we looked at we built a simple classifier of training images, digits 3 versus digits 7, and we built a simple classifier just by finding what an ideal 3 looks like and what an ideal 7 looks like, and then we built a simple heuristic that could classify the 2 digits. And we had over 90% accuracy just building that baseline. So that's something that's really exciting. When I was first reading Fastbook, it kind of blew my mind. So I hope it kind of had the same effect on everybody as well who were here last week. So, but today then we'll wrap up chapter 4, and we're going to look at stochastic gradient descent. Another thing, this week's format is going to be slightly different. I'm just trying to come up with the best format that kind of supports and is as we go week on week. I'm trying to improve the experience for everybody who's part of this call. So as part of that, for example, instead of using 2 screens, I'm using just the 1 screen. And I'll try and zoom in. I think last time there were some issues where I was quite zoomed out and people couldn't read what was on the screen. And something else we will do is we'll try and use majorly the clean version of the notebooks to understand things, to understand code. And as part of this session, we're gonna do that. So we're gonna spend more time looking at the clean version of the notebooks. Because I feel then the text could be distracting to everybody who's part of this call. So as we go forward, if there's comments, if there's feedback that you have, keep putting them in the Zoom chat or just in the as comments on the report that I'll share that we do every week. So with that being said, let's get started. So this week has been really, what we'll do this week would set us up for the whole of deep learning, and it will set us up for everything that's to come, whether it's NLP or whether it's computer vision or any other, anything that we do in deep learning would require something like a stochastic gradient descent or would require optimizers. And that's what we're going to cover today. As is usual for every week, go to this link, 1db.me/fastbook5. So if I go to that link, let's see. So I'm going to 1db.me/ Oh, I'm not going to 1db.me/fastbook5. It's taken me to some other page. But now I'm going to 1db.me/fastbook5. And that brings me to this report. So as part of this report, everything is everything the same. I'm not monitoring the Zoom chat. I'm only looking at the comments here. So you can just go here, click on write a comment and post comment. And then that way it's live. And this is where we'll be hosting most of our discussions for week 5 as well. This is exactly what we've done for the past 4 weeks. Cool. So then this week has been, I've got some exciting news to share. So if you're interested, majorly as part of Fast AI, as part of this Fastbook reading sessions, we're covering Fast AI, we're covering the basics of deep learning, we're looking into computer vision. But if Hugging Face and if NLP, natural language processing, if transformers are your thing, then Weights and Biases is hosting another study group. So it's being hosted every Sunday, I believe. Exact timings are here. So it starts July 11, 10 a.m. Pacific time. So you can have a look. That's 10:30 IST. I believe that would be PM, I assume. But have a look. Just convert them to your own time zones. And then if you go to this link, 1db.me/fastAIHF, that will take you to this meeting registration, and you should be able to register for the study group if Hugging Face is your thing and NLP is something you're interested in. We've had another exciting week, so thanks to everybody who've contributed. Thanks to everybody who've been writing about Fastbook week 4, and I do feel like doing this week over week, like I'm seeing the same number of people come up, and I'm seeing new people also come up, but then I'm seeing constant people who do write blogs, and I feel that is something really exciting for me, because I see I feel that that's the exact same process I was doing when I was doing Fast AI course for the first time. And I also feel that by doing this week over week and by being consistent, these few people will actually get the most out of this Fastbook reading session. So not to say that not anybody else who's not writing blogs won't benefit from Fastbook reading sessions, but because I went through the same process, and for me, this is what worked. I'm kind of biased that writing about what we learn as we go is kind of the best way forward. So Sai Amrit, thanks for writing a blog about Let's Keep Classification Simple. I think that's a really wonderful blog. I've read it. One of the best things that I like about this blog is he's used fast pages that Parul recommended last time. And it's really simple to get started with fast pages. So thanks, Sai, for writing about Let's Keep Classification Simple. And that's the blog. So Angelica, could you also please post all the links for all these tweets and all the reports in the Zoom chat? Thank you. We've also had Ravi, and these are people who've been writing week over week. So Ravi's come back again for week 4, and he's also written everything about that's the key points, and he's got his own blog, and he's sharing what he's been learning every week with us. So thanks, Ravi, for your efforts. Really appreciate that. We've also seen Kurian, so he's also been here. Has been writing almost every week that I've seen, and he's also come back and he's done a whole recap of week 4. So we built the MNIST digit classifier, and he's also got his own blog going, which is really exciting to see. And something I feel like I don't know how your journey is about blogging is, and this is not to say about Korean, but for everybody that's been blogging, something that I do is I find myself, if I wrote a blog about a year ago, and I have presented another talk about this, about publicly sharing your work, but something that does happen very often to me is that I've written a blog, say in 2019 or 2020, and I'm doing object detection in 2021, then what happens is I'd find myself going back to the blog that I wrote in 2020. And not only because I've written it, that's the easiest way for me to then have a recap because I'm the one who wrote it. And I also find myself referring my own blogs in the past. So if you are someone who's going to, by the time we finish and you want to see, okay, what did we do every week? Then you could very well go to your own blogs and you could have a look at what happened in week 1, what happened in week 2, and that could be a whole set of notes that you could refer. So I think I really, really encourage writing more and more blogs as we keep going forward. And thanks to everybody who've been doing it so far. Vinayak has come back again this week, and he's written about week 4 as well. So there's plenty of people who've been writing about it. I'm really excited to see this, and it's really good practice to do so. So Vinayak has got his own blog, which I would highly recommend checking out. And then we've had Ravi. Ravi's come back and he shared his blog. I particularly like the images that how he's defined that. I've read this blog as well, and I really like that how he's separated a RGB image into 3 channels, red, green, and blue. And he's provided a source for it, but it's just a really gentle introduction to how images are stored in computers. So thanks, Ravi, for sharing your blog with us as well. So that's with that being said, let's get started with stochastic gradient descent. And as I've mentioned, I'll be spending more time writing code this time, and we will come back to this OneNote PDF as we need to. But let's get started with gradient descent. Sorry, 1 second. I'm just trying to find where gradient descent is. Oh, here it is, 1.6. So we'll be referring. I will be providing on. As part of this chapter, we'll be covering what stochastic gradient descent is, and we'll also be looking at code as over here, and we'll be looking at how everything is implemented, and we'll implement it on the side. So that's how this session is going to look like going forward. And of course, we'll take breaks in the middle. If there's any questions that you have, keep posting them on at the Fastbook5, 1db.me/Fastbook5 link, and that's where we'll be. That's where I'll constantly look at. If I do believe that today could be a longer session, because my motive is to make sure that we cover and we wrap up chapter 4. If it goes above 90 minutes and you have to go in the middle, feel free to do so, because everything that we do cover is recorded. But I would highly appreciate if you want to stay around. I'm not sure exactly on how long it's going to take, but if it takes longer, then feel free to leave in the middle and come back to the YouTube video and have a look from where you left. So with that being said, let's get started. And when I say let's get started, and I've pressed something that's taken me to a different spot, thanks to the new setup that I have. And I'm trying to go back to stochastic gradient descent. Where is it? Oh, here it is, found it. Okay, so stochastic gradient descent then, what is stochastic gradient descent? Remember when we started with Fastbook week 1, and we saw Arthur Samuels way back in the 1900s, and he was sharing on how a machine could learn. So far, we've built a digit 3 versus a digit 7 classifier, but we haven't done any learning. Like we've just provided a set of rules. Okay, this is how it looks like. If something's closer to the ideal digit 3, then the new image is classified as a 3 and otherwise classified as a 7. But what we haven't done so far is we haven't done any learning, as in the model hasn't really been trained. So it's just a simple model that we used, which had no training. And as part of that, then we'll be covering stochastic gradient descent, and we'll see what stochastic gradient descent is. Then the two main things, if we want to start looking at stochastic gradient descent, the two main things are, the first thing is an automatic means of testing, which is written here. So because every model would have some weights, then we need to be able to see if the weights that we've assigned to a model, are they good weights or are they bad weights? So that means we need some automatic means of testing the weights, the current model weights. And the second thing that we need is we need a mechanism for altering the weight assignment. So if the weights are bad, then we need a way to be able to update the weights automatically. Like this is not something we should do, it's something the machine or the computer should be able to do on its own. So that's two main things that we need if we want to make sure that a computer can learn on its own. And let's see how we could do that. So let's say, remember last time when you were looking at, if in image 7, because everything is a number underneath, right? And if an image 7 looks something like this, and an image 8 looks something on the right, then if we have a look at this area, the one in green, if you have a look at this area, then for a 7, it's all background. Like there's nothing related to the digit 7 in the bottom right of the image. But whereas in the number 8, there is this section of the 8 that is in this bottom right of the image. So what if we have a weight matrix? And what's going to happen with this weight matrix is, what we ideally want is, we want this weight matrix to have higher weights, or to be activated more when it sees the digit 8. And when it sees the bottom right of the digit, then it needs to have higher weights, so it can give us a higher activation. So if we have something like a weight matrix, that's again a grid of the same size of image 7 and image 8. And if it has higher weights for this side when it sees 8, and when it sees 7, then in that case, for a digit 8, it's going to have higher numbers over here. Right. So that's just one way, and that's just one example of how we could get started. So let's say the probability of being 8, just as what I've shared, is just x star w times sum. So this is just as an example. X star w means this digits 7 or 8 being referred to as x, and the weight matrix being referred to as weight, or w. So then how does the stochastic gradient descent, or SGD, process look like? And this is just the overview of SGD. This is really, really helpful. And this is, it contains everything that we need to know about SGD. So the process of SGD looks like, the first thing we do is of that weight matrix, what we do is we initialize the weights. These could be random weights. These could be random weights. These could be pre-trained weights. These could be any values as far as we are concerned. But then the first step is you initialize your weight matrix with some weights, right? Then the second thing is, because now you have your weight matrix, or your model has some weights, the next thing is you can pass in some inputs to get some predictions. So that's the second step here. So you see, for each image, we use these weights to get the predictions. That's the second step. Then the third step is, now you have your predictions for all the images that you have, and you also have the ground truth label, so you know which images were digit 3 or which images were digit 7. Then you're able to calculate something called the loss, which we've already discussed what it is. So the third step is you calculate the loss. Then the fourth step is you calculate the gradients. This is something that's new. This is something that we're looking at for the first time. But essentially what the gradient will tell you is that if we change the weights, how the loss is going to change. So the loss and the gradient are related to each other. Okay. We will look into the details of this very soon, but for now, just understand that what the gradient will tell us, it will tell us that if we change the weight, then how is the loss going to change? Okay, that's been written here. How changing that weight would change the loss. The fifth step is you take a step. What does that mean? We started with some initial weights over here. What we want to do, remember, as part of the two things that we got started with, the first step is we want to check if the weights that we have, are they good or bad? And the second thing that we want to do is want to be able to alter these weights. We want to make them bigger or we want to make them smaller automatically. So the second thing, so this step is this idea of being able to update the weights automatically, okay? And we do that by using the loss function and by using the gradients. So we take a step. So that's the fifth step. It is written here in the book. You take a step, basically you update all the weights based on the calculations, based on the loss, based on the gradients that we have so far. And once you finally have, sorry, one second. And once you finally have a good set of weights, then you finally stop. So in the end, when you have a trained model, you stop. When you're happy with the performance of the model, that's when you stop. So that's what SGD looks like. So see what happens is if I repeat this process of making some predictions, calculating the loss, calculating the gradients of the loss, and then taking a step so that my model performance becomes better. If I keep doing this over and over again, then I'm going to end up after say 100 iterations or 50 iterations, I'm going to end up at a point where the model performance is high. And then I can say, I can be satisfied with that model performance and I can say it's time to stop and my model has finished training. So that's the general idea of stochastic gradient descent. Below then in the book, this is every step has just been explained in a bit more detail. As I've already said, initialize means you initialize the parameters to some random values. Loss, what is loss? We've already looked at the difference between the loss and a metric. A loss is just a number that will tell us about the the loss will tell us about the model's performance, right? We want to be able to assess that the weights that a model has, are they good or bad? So see this. This was my model, right? And each model would have some weights W, right? I need to be able to tell if these weights that this model has, are they good or bad? And then something that will help me understand this is called loss. So loss is that one thing that will help me assess. If the loss is a number that's generally high, it means that the model performance is bad. And if the loss is a number that's generally low, then that means the model performance is good. So then so now you've initialized your weights and you have calculated the loss. Then the third step is you take a step. So you take a step to update the weights, right? And this step will basically, you only take a step to update the weights that you know is going to improve the model performance. How do you know that? You know that through the gradient. And we will look at this as we go forward in the chapter. But for now, just understand that when you're taking a step, you're basically taking a step to improve the model performance. And you keep doing this over and over again, and you finally stop. So that's that. So that's just an overview of what SGD looks like. So let's understand this with the help of images. So let's say I have a loss function that looks like this, that looks like x squared. And if you plot that function of x squared, it looks something like this. In mathematics, this is a parabola, upward looking, but you don't have to worry about that at all. Just use this plot function in the library, and FastAI has this function called plot function. And then you can use that plot function to plot any function. And if we plot this, then you can see that it looks like this curve that's upward looking. Okay, so then the first step, as I said, in stochastic gradient descent is to random initialize, right? This is my first step. So as part of my first step, if I randomly initialize, then let's say I'm somewhere here on the loss curve, right? So I can randomly, if this X represents the parameters, just as an example, if this represents the model parameters, then let's say if I initialize my value, the first value at somewhere around minus 1.6, then the loss would be somewhere around 2.4. Does that make sense? So that's just my random initialization. It could be any number, but I just randomly initialize. Then, as I said, the next thing that you want to do is you want to be able to calculate the gradient. So think of this. If I'm somebody who's trying to reduce the loss, and that loss looks like this upward looking curve, and I want to reduce the loss, right? Then this value of parameter, I should move in this direction. Basically, to bring this loss down, I need to update the value of X such that it's more closer to 0, right? Because that's when the loss is the lowest. But right now I'm at minus 1.6. So I need to go towards 0. I need to update the value of this parameter X towards 0 such that my loss can decrease. And then how do I know that I need to go, like, for a human, I can just have a look at this image and I can say, oh, I need to go towards 0 so my loss will decrease. But how does a computer know? How would a computer know which direction it needs to go? That's something that a slope can tell us. Okay. In mathematics, then just think of this: the slope or the gradient will tell you the direction that you have to move, and it will tell you the direction that you have to move to reduce the loss. Okay. So what this slope is telling me, the slope looks like this. What it's telling me is that I need to go from this point towards the right so that I can reduce my loss. Okay. So that's another step in stochastic gradient descent. That's the third step, actually. So when I say that's the third step, it's basically I'm referring to this. I initialized, I made some predictions, I calculated the loss, and now I'm calculating the gradients. So the slope will tell me which direction I need to move to be able to reduce the loss. And then if I make a step in that direction, so if I was here previously, this is where I started. If that's my starting point, I'm just going to call it S, which is my starting point. And if I made a step in this direction, then as you can see, my loss has decreased. So if my loss was a higher value, now it is some lower value. And that is what SGD does. SGD is just a way of automatically reducing the loss. Okay. And if you keep doing that, if you keep following this process over and over and over and again, you're going to come to a point where the loss is a minimum. And when your loss is the minimum, your model performance is high. And when your model performance is high, that means it can do the task you're asking it to do. So if you're training a model for cats versus dogs, and initially the model has really bad performance, it cannot classify cats versus dogs. That means the loss is really high initially. But then if you start taking these steps towards the gradient, so you start taking these steps towards the slope of the loss, then you know how that loss is going to, as in you know the direction that you have to move to reduce the loss. And if you keep doing that over and over again, you're finally going to reach a point where the loss is the minimum and the model performance is the highest. That means that now your model can classify cats versus dogs. So that's the basic idea of SGD. What time is it? It's I'm going to take 2 minutes break, and I'm going to look at the questions. If there's any questions that are related to what we've looked at in terms of the basic idea of SGD, that's what we'll look at now. So 1 second, please. Okay, we have some comments. That's okay, Durga. Higher activations, just ignore that for now. As long as you understand that SGD is just the process of being able to move in the direction of the gradients, and SGD is just this process of being able to reduce the loss iteratively, then that's good enough. As long as you get the main point, then don't worry about this, because everything will become clear as we go, and we're going to dig deeper and deeper. And my apologies for using the word activations without telling you what they are. So ignore me for now. weight initialization, when he's talking about randomly initializing the parameters, it does mean picking completely random numbers. Yes. So weight initialization, everything that I'm explaining right now, we're going to look at in terms of code. So that's okay if you only get some part of it, but as long as you get the basic idea. Weight initialization could just mean if you have an array of 5 numbers, then you just initialize those 5 numbers to be some random values. So that's just weight initialization. That just means you're picking some random numbers and you're assigning those random numbers to the parameters. So I'm now looking at the next question. When validating error is increasing after number of iterations, it was told that the model tried to remember the training data. Yes, it's still out of my intuition how a model which uses data to learn also remembers data. Okay, like model is not thinker, how it remembers. Little awkward for me to think on that. Okay, so you're referring to overfitting. What I would recommend is have a look, and what I would recommend is just read more about overfitting on what that means. But basically, the model is not a thinker, yes, but if you keep reducing the loss and you keep over time, when you're going over the input data, what you'll see is all the model is doing, it's starting to learn the patterns of the input data. Okay, and if you keep going over and over and through multiple iterations, then what it's going to do is it's going to remember those patterns. The model's going to just overlearn all those patterns, and then it won't be able to class. Like, you want the model to learn general patterns. You don't want the model to learn the exact patterns. An example of this is if you're trying to classify, say, a particular cat from a particular dog, then each cat of the same breed are going to look different. Like, they could be in a different pose, they could have slightly different color of the fur, they could have some slight small variances, right? But if you keep training your model over and over again, then what the model will learn is it will only learn a particular type of fur. It will only learn a particular type of, like, if the cat is sitting in a particular position, that's what it means that the model has overfit. It just means that the model has learned everything that there is to learn about the single image. Instead, what we want the model to learn is we want it to learn the general pattern that cats have furs. This is what the furs look like. And that's just the basic idea of, so I think what you're referring to here is overfitting, and I hope what I've explained would help. Our gradient descent, and for now, let's just assume stochastic gradient descent and gradient descent are the difference. So don't worry about the difference between gradient descent and stochastic gradient descent. Stochastic gradient descent is just through mini batches. But that's okay. Don't worry about these small things for now. Let's just get the basic idea. And as we go forward, we will understand every small thing that there is to know and all the small differences as we keep going further and further into the fastbook sessions. Is this similar to finding the argmin for the parameter? No, it's not the same as just finding the minimum value for the parameter. You're just trying to minimize the loss. So what argmin does is argmin just calculates what the minimum value is. So that's completely different than what we're trying to do. We're trying to go over and over in iterations, and we are trying to update the parameters in a way. So going back to the image, we're trying to update the parameters in a way that your predictions match the ground truth variables. And when your predictions match the ground truth variables, that's when the loss is at a minimum. Okay, so that's the basics of stochastic gradient descent. Now, something, as I've said, in stochastic gradient descent, what you need to be able to do is you need to calculate the gradients, right? So you start with, again, to repeat, what happens in stochastic gradient descent is, or generally in any deep learning, is you start with some initialization or some random values, you make predictions from the model, you calculate the loss, then using that loss, you calculate the gradients. And that gradients is the slope that we saw before. Now, how do we calculate the gradients? Like in calculus, there's derivatives, right? In maths, derivatives can help you. And that's how you can calculate the gradients. But when you're in code, you don't need to worry about the mathematics. Sure, it will help to understand the basics of what gradient means and what slope means. But if you go back, when you go back and you read this chapter, you'll see that there's lots of resources in Khan Academy that have been provided as part of this chapter to help you with the basics. But for now, for what we want to know is, let's say I have my loss function, which was x squared, right? So I can just say plot, or I don't need to say plot function. Actually, we all know that this x squared looks like this, the upward looking parabola. So then in PyTorch, if we want to be able to calculate gradients, then all I need to do in PyTorch is I need to be able to say that starting with some number, if I pass in requires grad, then PyTorch knows that this number, anything that I do to this tensor rather, PyTorch will keep a track of everything that I do to this tensor, and it will know that later I'm going to come back to this tensor and I need to be able to find the gradients with respect to this xt. Okay, so let's see let's assume that my input to this function f is this tensor 3, and I've already said that this tensor 3 I need to be able to calculate the gradients. Okay, so I start with that. And in PyTorch, you can see how now in xt it says requires grad is true, which means PyTorch knows that it needs to calculate the gradient, so it needs to be able to calculate the gradients on this xt. So now I can get my output. So yt. So if I pass in 3 to x squared, I will get the value 9, right? So I can calculate my yt. Now, to be able to calculate the gradients, the function call that you tell PyTorch to calculate the gradients is backward. So when I say yt.backward, it's going to go backwards and look at all the function calls that we've made to this number xt, and then it's going to calculate the gradients with respect to xt. So if I go yt.backward and I now check xt will have basically an attribute called grad, which is the gradient of xt. So if I press xt.grad, the gradient is 6. So in mathematics, if you come from a mathematical background, you would know that the derivative of x squared is 2x, right? And then if the input is 3, which means the gradient would be 2 times 3, which is 6. So all I wanted to show as part of this is that you don't need to worry about how to calculate the gradients. PyTorch can do it all for you. So when we're at this step in stochastic gradient descent, I'm trying to find the figure again of the whole process. So here's the process. So at step 4, when we need to be able to calculate the gradients of the loss with respect to the parameters, then you don't need to worry about how that happens. For now, just to be able to do all of this, you can just say loss.backward, which will calculate the gradients for you. So that's the basics of it. So let's say if my input, instead of being just one tensor with a single number 3, let's say my input was this number 3.4 and then 10, or just some floats. I remember what my fx looks like. I can just say my yt. So my output, I pass in my input and I just get my output. So my output is some value. Then I can again say backward, because this tensor has been initialized to say, hey PyTorch, I need you to remember that I need you to know that I want to be able to calculate the gradients with respect to this xt. So I can just say now my output.backward or yt.backward, and I can check the gradients. They're 6, 8, and 20. So remember, because the input function was x squared, the gradients would be 2x, which means for value of 3, the gradient would be 6. For value of 4, the gradient would be 8. For value of 10, the gradient would be 20. And that's it. So again, to repeat, PyTorch can calculate the gradients. You don't need to worry about being able to calculate the gradients. So that's the basics about being able to calculate the gradients and using PyTorch. Now we move to our next thing that we need to know is stepping with a learning rate. 1 second. Sorry, 1 sec. I've just got a technical thing I need to solve. Okay, all good. So then the next thing that we need to be able to look at is what is a learning rate, right? So far, what I've told you is that calculating the gradients will tell you the direction that we need to go to be able to reduce the loss, right? So when we calculate the slope at some point, so going back to the figure, if I started at this point here, then the slope tells me that the direction of the loss towards the minimum is in that side, which means that I need to update my value from here and I need to go on the right towards the value 0, as we saw. So this slope is just telling me the direction. It's not telling me what is the magnitude, like how big should my step be, right? So I know that I need to update my parameter towards the right side direction, but I don't know like how far do I need to go? Do I go from here all the way to here, or do I go from here just till this point, small point B, or this point C, or do I need to go all the way to point D? So that's something that the learning rate will tell us. So going back to the learning rate, as I said, in stochastic gradient descent, then when you calculate the gradients, you update the weights, right? And how do you update those weights? You just say that my weights are weights minus equal to gradient W star LR. So if I'm to write that, then that's just that my updated weight, I'm going to call it W dash, is equal to the initial weight W minus learning rate star the gradient of W. Okay, and as I've already said, you can calculate this gradient using PyTorch, TensorFlow, or any library. Basically, libraries can calculate the gradients for you. So this LR refers to the learning rate, right? So what I'm saying is, I want my updated weight, it's my initial weight minus LR star grad. So gradient times LR is the amount by which we move. Okay, so until now, I knew the direction in which I need to go. Now the learning rate is telling us the amount by which to move. Something I wanted to share, if you want to run experiments as part of this and you want to write blogs for your next week or for this week, try removing the LR from this equation. And an experiment here could be to remove LR and see what happens. So see how the stochastic gradient descent would behave if you just remove this learning rate parameter. I think that will really help anybody who's doing this experiment to then understand the importance of LR. But for now, let's just understand that LR is just telling me how far my step needs to be, okay? So if LR, but I need to be careful with this LR, okay? I need to be careful with this learning rate. So if my learning rate is really slow, so let's say this is where I started, right? This was my random initialization. So I'm just going to call it random init. So this is my point A is where I started, okay? Now I already know that I need to make a step in this direction, okay? If my learning rate is really small or it's really low, then I will only make a tiny step. So the tiny step will take me from here, point A to point B on the loss curve. And then I will make another tiny step to point C, another tiny step to point D, another tiny step to point E, and so on. So you see how I need to make so many tiny steps to reach the lowest point on the loss curve, okay? The problem with this is you're wasting computation, or it's going to take you very long. You have to, if ideally it would take you like 10 iterations, then because your learning rate is so slow, you would have to do like 1,000 iterations to then reach the lowest point on the loss curve. So you can't have your learning rate be very low. You also can't have your learning rate be too high. If the learning rate is too high, and let's say I started at this point, okay, I already know that I need to make a step in this direction. But if my learning rate is too high and I made a too big a step, and instead of going from point A, I went to point B, then on the loss curve, I've made my loss bigger. So if my loss had a lower value, this is my lower value. Now my loss has a bigger value. And then if I make a bigger jump again, then I've landed at this point and my loss is again higher. And then I make a bigger jump again to point D and my loss is again higher. So you can't have the learning rate be too high either, because then your loss is just going to go bigger and bigger and bigger. Or your loss is going to bounce around. So if you started at point A, ideally what you want to do is you want to go to this point B, then this point C, and then finally this point D, right? So you'd reach the lowest point of the loss curve. But if your learning rate is too high, you start at this point, then you go to this point, then you go to this point, then here. So all you're doing is you're jumping around in the loss curve and you never reach the bottom. Because to reach the bottom, then you need to have perfect size steps. So you see how learning rate is a really, really crucial parameter. And in FastAI, there's something called the learning rate finder. I shouldn't have said it, but I will say it still. As we go forward, you'll see a learning rate finder example, and we will look at that when we look at the pets chapter next. But basically what this learning rate finder tells you is it tells you a good learning rate or how big your steps should be. It gives you some intuition, or it gives you some idea on what the steps should be. But the steps that you have to make towards the lowest point of the loss curve, they can't be too high or they can't be too small. That's the basic main thing that you should know from this example. Okay, so now we're ready to look at an end-to-end SGD example. So we are now ready to look at the end-to-end SGD example. So here it is. So just to recap, my SGD looks like this. I start with some initialization. I make predictions. I calculate the loss. I calculate the gradients on the loss with respect to the parameters, and then I take the step. This step depends on this parameter called learning rate. If the learning rate is too high, then I've made the wrong step. If the learning rate is too small, then I'll have to make many steps to be able to minimize the loss. And then once finally I've reached the lowest point on the loss curve, then I stop. So that's my stochastic gradient descent. Okay, so now we're looking at an end-to-end example on SGD. So let's say my time, let's say I only have some numbers from 0 to 19, and I refer to that as time. These could be 20 seconds, the first 20 seconds. So let's say that's time, okay? And let's have speed as some value of this time. So if I plot them, this just tells me that at time 10th second, my speed was somewhere around 5 or at the bottom. But this is just the curve that we have to fit. Like we want to train a model that can then predict this time and speed curve. Okay. Now, in SGD, or forget SGD, let's just say that my model only has 3 parameters. So the 3 parameters that my model has, I'll zoom in a little bit just let me know if this is too zoomed out, but I'll try and zoom in a little bit. 1 second. Let's try this. I hope this is better. So let's say now my model has only 3 parameters, A, B, and C. Okay. Then I can define my model as being AT squared plus BT plus C. Basically, it's just an equation. It's just a quadratic equation. But let's say this is what my model is. It only has 3 parameters, and the model function, remember, from deep learning, you already know that a model is not something magical. It's just a function. Okay, and let's say right now my model is just this function f that looks like AT squared plus BT plus C. Then I need to be able to calculate the loss, right? So if I have some inputs and I can pass those inputs to this function f, I will get some predictions, but I need to be able to calculate the loss. Let's say I'm using a loss as MSE, or the mean square error. Without telling you what it is, let's just say this is what the mean square error looks like, and that's just my loss function. Without going into the details. But for now, just to get the basic idea and just now to get the basic understanding of SGD from the viewpoint of a code. So because my parameters were 3 numbers, I can initialize them. I can say, so torch.random, these are things you should, when you go back and you're looking at this clean version of the notebook, just create new cells and type this, okay, and see what that does. So every time I press this, it's just returning 3 random parameters. If you want to check the documentation of this, you can press question mark at the bottom. That will bring up the documentation like this. Or if you want to look at the source code, you can press double question mark, which will bring up the, basically, then it will bring up the code as well. So let's say then, so as I said, my parameters are just 3 numbers. So the first step in SGD was to be able to initialize my parameters with some random values. And I say requires grad because what we want to do is we want to update these parameters based on the gradients, right? Because these are the model weights. What we want to do is we want to update these model weights based on the gradients. So we have the perfect model weights so that the model performance is high. So that's what this step is doing. It's just initializing parameters. Step 2 is I want to be able to calculate the predictions. So I can pass in to that function. I can pass in those values of time, and I can pass in the value of the parameters. So remember, from deep learning images that we've seen before, a model gets 2 things. It gets some input and it has some weights. So these parameters are the weights. So I can get my predictions, and the predictions look something like this. It has a gradient function. Okay, this is just telling PyTorch that I need to be able to calculate the gradients. So now I can plot my predictions. So the blue is the actual line of the time versus speed. The red is what this prediction looks like. The third thing that I can do is I can calculate my loss. So I can pass in my predictions, and I can calculate the actual values of speed, which go in here, and I can calculate my loss. So see how loss is a random number and it has a gradient function. Okay, so when I say loss dot backward in the next step, then the parameters get a attribute called grad, and the grad have some values. So now my each parameter has the value of the gradient. So this gradient is just telling us, if you, from everything that we've learned so far, by calculating the gradients, we know which direction we have to go. The next step that we have to do is we have to take a step in that direction, right? So when we take a step in that direction, that stepping in that direction, given my learning rate is some value 1e neg 3, that's just 0.001. So let's say my learning rate is that value. Then I can take a step in that direction. Remember how the step in the direction looks like? It was W, trying to find that stepping in that direction in my notes, so I can refer to that. 1 second. Where is it? Somewhere at the top, maybe. Can't find it. All I'm trying to do is I'm trying to show the stepping on the formula for that stepping is. So let me see if that was, I think it was somewhere lower, somewhere at the bottom. There it is. So see how, so when we were taking the step, that's what the step looked like. My updated weights are, if you remember, my updated weights are this value, W minus LR star grad of W. So this is what it looks like. My updated weights are my initial weights, so I can just say minus equal to. So my initial weights minus LR times the gradient. Okay, so this is just SGD, and now we're updating the parameter weights. So let's do that. And then we get the predictions again, and we can calculate the loss. So see how the loss this time is 343, and the loss previously was 371. So just by taking one step, we've been able to reduce the loss. So if my loss was a curve that was a upward looking parabola, I've made a step in the direction that reduces the loss. So I can now show my predictions. It's still bad, but it's just one step. Like we've only taken one step. So now I can make all of this as a function. Basically, we get the predictions, we calculate the loss, we say loss.backward to Python, or sorry, to PyTorch. In that way, it can calculate the gradients. So when it has the gradients, I can now update my parameters, and I can say they are minus equal to LR times gradients, and then you just print the loss. So if I do this 20 times, let's do it 20 times. See how I started with a loss value that was 343. I've ended up with a loss value that's 26. So let's plot that. So right now, this still doesn't look really good. So let's do it 20 more times. And now you can see how my red, which is the predictions, it's trying to match the exact values of the time versus speed. So this is, I hope that by doing this, now we can stop, because we can stop now, because now the loss is at a low value, and now we know that this the predictions are looking good, and the predictions are finally, like, they're matching my expectation and the model performance is high. So this is the overall process of stochastic gradient descent. And I've just shown you how it looks like in code. So when you go back, when you're going back and you're looking at this clean version of the notebook, make sure then in your head that you're able to match all those steps to, I'm trying to find the stochastic gradient descent image. Yes, make sure that you're able to match all those steps that we've just had a look at over here. So these steps of, so this step one of initializing the parameters, calculating the predictions, calculating the loss, calculating the gradients, making a step on the weights, and then repeating the process. So make sure that you're able to have a look at these 6 steps and you're able to match them to what we saw with stochastic gradient descent when we first started. So that's stochastic gradient descent. Any questions? I'll take 2 minutes for questions on stochastic gradient descent. And then after this, what we will do is we will use stochastic gradient descent to calculate our MNIST classifier. So until now, we've only created a classifier based on some rule, but we didn't do any training. But now we can use stochastic gradient descent to calculate to classify 3s from 7s. So let's see if there's more questions. If learning rate is too high, can we detect that in training and repeat the last step with a smaller LR? Okay, so if learning rate is too high and you've already made a step, then your parameters are already at a bad value. You will have to, unfortunately, unless you have the last epoch's weights or unless you have the last weights, you will have to restart training. But you can definitely detect that because your loss is going to diverge. So if your loss in the first epoch was, let's say, some number 4, then if your learning rate is too high, it's going to go to that number either 6 or it's going to be like 4.5, or it's just going to continue bouncing around. So if you see over time, over multiple epochs, your loss isn't decreasing and your loss is basically increasing or it's diverging, that's when you know the learning rate is too high. But as we train more and more models, so right now it's just giving us the basics of MNIST or doing image classifier, digit classifier. In the next chapters, as we go more and more deeper into computer vision, we will train more and more models. And then as we train more and more models, all of these things will become clear. We'll get more intuition about how things look like. Can we keep changing the learning rate? It looks like a good idea to have a larger learning rate in the beginning, but as we get closer to the minimum, we use a smaller learning rate so that we don't overshoot the minimum. Ravi, you're 100% right, and you've caught the pulse of it. But 100%, it definitely makes sense to have a bigger learning rate at the beginning and then a smaller learning rate, or there's like different, what you're referring to of being able to update the learning rate as we go through different epochs is referred to as learning rate scheduling. There's multiple schedulers. So if you search learning rate scheduling in its learning rate schedulers PyTorch, this will bring a big list of, it'll take you to torch.optim, it will bring you a big list of the different scheduling that you can do. But this is definitely a good idea. A question to Aman, what extensions do you have for notebooks? I'll cover this later, but I will come back to this. Sayam. In FastAI LR Finder, we usually have a minimum and maximum learning rate. What is the ideal learning rate to choose from it? We will get to this question when we get to the FastAI LR Finder. I'm going to skip on this for now. Hi, the loss after 20 iterations and the total loss after 40 iterations are closer values, and yet the model is performing much better. Can you explain how? Thanks, Rahul. I think it's yes, the loss is much better, and I think what you're referring to is the stepping. So when we started after 20 steps, the loss was 26, and when we started after so it's basically the same thing. Like I've still done, what I've done is I've done the mistake of plotting when I did the show preds the first time, it wasn't actually showing the predictions for this lower loss. So it's just a mistake on my part. If you delete this and you run this notebook on your own, you will see that you don't have to run it for 20 steps again. So I've just made a mistake in that little section of the code. But you can ignore that. You're 100% right in catching it, but it's a mistake on my part. How to decide that the loss is minimum and it will not go below this? There's no good way to decide that the loss is minimum. But basically, if you do multiple epochs and your loss is continuing to decrease, right? You keep doing that. So if your loss is still decreasing, which means you still haven't reached the bottom part of the loss curve, right? So if you're, so say if you're somewhere here and your loss is still decreasing and you get to this point and your loss is still decreasing. So when you're at the lowest point, after that, the loss will not decrease any further, right? So your idea is then, as long as your loss is decreasing, you keep training the model. Unless the loss starts to diverge, that's when you know that you have to stop training. Okay, so that's the basics for SGD and how SGD looks like in code. So let's move on. Okay, so now let's use SGD to be able to classify my MNIST digit 3 versus digit 7. So remember when I had my stacked, well, my 3 is basically if I take the first element from all the 3s that we had. Actually, so just to give you a background so far, now from section 1.7 onwards, we're just going to apply what we've learned about stochastic gradient descent. And we're going to apply that and we're going to use it to be able to classify 3s versus 7s. Okay. So my first, if I just take the first element of all the 3s that I had and I plot it, it looks like that. And I plot my number 7, that looks like this. Okay. Then all my 3s, remember we've already covered this last week. I put them in a tensor. So all my 3s are now stacked. This stacked 3s is just a tensor that looks like 6131 by 28 by 28. What does that mean? I have 6131 images of the number 3, and each image has a dimension of 28 by 28. So this is my 28 width, and this is my 28 height. Same for stacked 7s. I have 6265 number of 7 images, and each image has a shape of 28 by 28. So this is my width, this is my height. Okay. So then my training variable, I can put them all in one list, and let's see what I get. So when you're running back this notebook by yourself, try doing just this part first. So if I do this and I check the shape, all I'm doing is I had 2 things, right? I had my stacked 3s and I had my stacked 7s. I can put them together in one tensor. So if you add 6131 by 6265, that will give you 12,396 images. So we have 12,396 images in total, and each image has a shape of 28 by 28. In PyTorch, when I call, excuse me. Sorry, one second. Sorry, guys, I'm back. Just have a bad cough these days. So when I say dot view -1 28 by 28, all I'm saying is whatever the shape of this is. So let's see what the shape of this is. So it is 12,396 by 28 in my second axis and 28 in my third axis. Okay. All I'm saying is ignore the -1 for now. What I'm saying is you reshape this tensor such that the last axis has a shape of 28 by 28. So how is that going to happen? All it's going to do is it's going to store this 28 by 28 as one vector now. So if I do that, then my final shape of the train X looks like 12,396. But instead of having 2 X's with width and height, now it's just a single vector. So let me show you what that means. If I look at the 0th element of this, see how it's still a matrix, okay? Whereas if I look at the 0th element of the reshaped version, instead of it being a matrix, it's now just a long vector of length 784. So these are things you should be able to do when you're running these notebooks by yourself. Okay, so now I stacked my 3s as the first part and then my 7s as the second part, which means I can have my label. My 1 would be times length of 3s plus 0 times length of 7s. What does that mean? That I will have 6131 ones in my train Y and 6265 zeros in my train Y. So for 12,396, the first 6131 images are threes, which means the first 6131 tensors in this train Y are value 1. So let me show you that. Train Y until 6131. See how they're all 1. And then after this, they're all going to be zeros, right? Because that makes sense, because we just stacked my 3s and 7s, and my first 6,131 with 3s. Okay, now we're looking at what is a data set. In PyTorch, you can just say list and zip, and you can pass in to basically train X and train Y. When you do this, then your data set becomes a list, which is zipping through train X and train Y. And when you go and you check the first item of this, it will return the first item from X, and it will return the 0th item from Y. So my first item from X looks this long, which is 784 vector, and my first item from Y looks this long. So finally, I have my independent and my dependent variables. So I can just check the shape. So my X dot shape is 784, which represents the first 3-digit. So the first image of digit 3, and because it was 28 by 28 and we reshaped it, so it has a shape of 784. And Y has a value of 1. I can do the same thing for my validation set, so I can get a validation data set. Now, next thing you want to be able to do is when we be able to initialize the random. We need to be able to initialize the variables using random weights. So I can just use torch.random to be able to initialize the weights. And I say requires grad because I want them to be parameters and I want to be able to update and calculate the gradients. So I initialize my weights using this function. I initialize my bias. And then this is what my model looks like. So if I'm doing classification of digit 3s versus 7, I'm just trying to use a linear layer. So what's a linear layer? In mathematics, ax plus b represents a line. In PyTorch or in deep learning world, you'll see that this is being referred to as a linear layer. So I just say that my prediction function right now is just this linear 1. So what does the prediction function do then? I can pass in my independent variables or my X items basically to get some predictions. And here it is, I get my predictions. So if I have a look at the preds.shape and train X dot shape, then for every 12,396 images that we input, we get some predictions. So if I want to check if the predictions are correct or not, this should be 0.5. There's an error in the notebook that says 0. I can check the value of my corrects, and I can check the float. So what does this mean? What am I doing at this point? So see how I had a prediction that looks like this, right? If the value is a 3, then my ground truth label is 1. If the value is, if my ground truth label is 0, then the number was a 7. Remember that. So when I do something like preds greater than equal to, or preds greater than 0.5, so if my prediction is greater than 0.5, then that means that the model is trying to say it's a digit 3. If my prediction is less than 0.5, then that means that the model is trying to say that the prediction is 0. So I can then check my accuracy just by calculating the mean. I convert everything to a float, and I can say mean, and I can calculate the item. Without saying item, it would have returned a tensor. In PyTorch, you can just say item, which will convert that tensor into a number. So until now, all I'm using is just PyTorch. If there's parts of this that you don't understand, then that means you need to go back and you need to learn PyTorch and you need to learn more about Python. So practice more and more about every code line that's written so far. Okay. All right. So now I can get predictions. So now going back to the notebook, something I want to share without going into the code for now. Okay, here we are. Okay, so So this is where we ended up in our notebook, right? So what's the difference until now? What have we done so far? So let me try and summarize that. Oop, 1 second. So let me try and summarize that over here. What we have done so far is we have a model that looks like this linear one function. We provided it with some weights and we passed in some input. So remember the init weights function, init weight function. That's what's initializing these weights with some random values. So I initialized this with some random weights. I passed in the input. In code, this was called as train X, and I get some predictions, right? Now, to do SGD, so far all good, right? This is exactly what we've done in code so far. But to be able to do SGD, I need to be able to then calculate the loss, and then I need to calculate the gradients, and I need to do the stepping and all that that we've looked at before. So we need to define a loss function that we can then call backward, and then we will update these weights based on the gradients so that the loss becomes lower. So let's do that. We haven't defined the loss function so far. So that's what I've written here. So far, we have not defined the loss function. We need to define a loss, and then we can calculate the gradients and do SGD. So let's try and create a loss function. In code, so I'm using this PDF version now. I'm not going back to the code. I will go back to the notebook in just a sec, but I need to be able to explain how a loss function is defined. So if I have my targets, which is 1, 0, 1, and let's say the predictions that the model makes are 0.9, 0.4, and 0.2, then my loss function could be torch.where targets equal to 1, 1 minus predictions, or otherwise predictions. Okay, now let me try and explain that. So if I have some inputs, if my targets were 1, 0, 0, 1, remember we converted everything. My targets were just zeros or ones, right? And let's say the predictions from the model are 0.9, 0.4, and 0.2. Then what is this? Excuse me. Then what is this MNIST loss function going to do? What this tells us, what is this? It says if targets equal to 1, then my loss is 1 minus predictions. Else, that is basically saying my target, that is just basically saying my target is 0. In that case, my loss is equal to predictions. Okay, so why could just this be a loss function? Okay, why could this be a loss function? So let me try and explain that. So my predictions, let's say if I'm somewhere here, my 3s, let's say, are here, my 7s are here. So let's say my 3s are represented as the label basically the tensor 0, and my 7s are represented as tensor 1. Okay, then if then I need to be able to know, basically I want my predictions for 7s to be close to 1, and I want my predictions for 3s to be close to 0, right? That's how I know that my model is accurate. But let's say if the model makes predictions everywhere, like this is where the predictions are. Okay, so this is a prediction for 3, this is a prediction if actually the image was 7, this is again a prediction if the image was 7, this is a prediction if actually the image was 3, and this is a prediction if actually the image was 7. Okay, so what we want to do, instead of the model, this is a poor model. What we want to do instead, if this represents my 3s, this represents my, what we want to do is we want all model predictions related to 3 to be closer to 0, and we want all model predictions for an actual digit 7 to be closer to 1, right? So we need to be able to define a loss function that can say that, hey model, these predictions that you're making, these are bad predictions, because that's how then we know that the loss is bad, and that's when we can calculate the gradients, and that's when we can try and reduce the loss. So if you're trying to say to this model that these predictions are bad, then a simple loss function could just be the distance of how far my predictions are from where they should be. So if I calculate with respect to sevens, I can see that this prediction is this far, this prediction is this far, and this prediction is this far, right? So these predictions are very far away from where they should be. What I want to do is I want to minimize this distance, right? Or for threes, this is the distance, and this is the distance for this prediction 3, right? What I want to do is I want to be able to minimize the distance, okay? So in that case, I can define my loss function as if the actual image is a 7, then my loss is 1 minus prediction. Okay, so 1 minus prediction would give me all these distances for 7. So that gives me basically the distances for 7s. And when the actual digit is a 3, then I can just say my predictions, my loss is equal to predictions, because then that will give me these distances. So it gives me this distance of 3. And then once I have the loss, then all I have to do is I have to minimize this. I hope this helps. This hasn't been explained in this much detail in the book, but I wanted to make an effort to try and explain the loss function that we have so far. So that's why this is a loss function. And basically, when you represent this in code, it can be just a single line. So tosh.where targets are 1. So tosh.where targets are 1 refer to everywhere where it's actually, say, a 7. That's when your loss would be 1 minus predictions, because 1 minus predictions will give you the sum of all of these, like how far, because these should be closer to 1, right? So then the distance is telling me how far it is from 1. And otherwise, you could have just said over here, it could have been 0 minus predictions, which wouldn't make sense. Or you could just say predictions minus 0, which wouldn't make sense either. So you can just say predictions. So that just means this is how far it is, how far my predictions are from 0. So that's why this is how this MNIST loss has been defined. So if I calculate the loss on, let's say my targets are this and my predictions are this, then if I calculate the MNIST loss, then that's how that gives me some. So this is the sum of distances, or sorry, it is the mean of distances, my loss function. So once I have all the distances, I can just calculate the mean. So this is what my MNIST loss looks like. And the key thing then to note, here is, if I remove the mean, let me show you. The key thing to note here is when your prediction is 0.9 and the actual value is 1, then your loss is 0.1. When your actual value is a 0 and your prediction is 0.4, then your loss is 0.4. When your actual value is 1 and your prediction is 0.2, then your loss is 0.8. So when the model is actually closer to the actual value, excuse me. So when your model is actually closer to the actual value, that's when the loss is lower. But the further away you go from the ground truth value, if it was a 1 and you're somewhere here, that's when your loss is the maximum. So that's the intuition behind this loss. So that's how MNIST loss has been defined. But there is a problem with this loss function. The problem is this assumes that all my predictions are between 0 and 1. That wouldn't always be the case. Why? Because remember, my model was just this ax plus b. It was just xb at the rate weights plus bias. So at the rate function in PyTorch represents matrix multiplication. And when you get the predictions using this function, then if you think of it in terms of mathematical terms, then a linear line could be just like this. So it's not always that all my predictions would be between 0 and 1. They could be higher than 1 or they could be lower than 0. So how do we fix this? There's a function called sigmoid. So that's what the sigmoid function looks like. What does this sigmoid function do? It basically, this sigmoid function looks like this, and it basically, all it does is it converts all my predictions between 0 and 1. So that's what this sigmoid function can do. If my value is really high, like let's say 1,000, then in that case, it will just be like a value of 0.99 or closer to 1. And if my value is like -4, then it's closer to 0. So it converts my whole thing into zeros and ones. So I can then update my MNIST loss function. First, I can take the sigmoid. So that means that now, I'll just write it here. At this point, after taking the sigmoid, my predictions are between 0 and 1. So this, after taking the sigmoid, then I can be sure that all my predictions are between 0 and 1. And then that's after this, I can just apply this distance loss function that I've explained. And that's it. Now we are ready to do SGD. But I will take questions for 5 minutes on basically if you have any questions about how this loss function has been defined. How to decide the loss is minimum and will not go below this? I see that Pred's values were not between 0 and 1. So does it make sense to keep the threshold for Pred as 0.5? Thanks, Bhavni. I think that's a great question. And I hope taking the sigmoid will now answer this question. Because when we're taking the sigmoid, then that makes sure that all my predictions are between 0 and 1. This explanation of loss function is phenomenal. Oh, thanks, Grijesh. I'm glad you I'm glad it's explained, like it helps. Okay. So now that we have everything, now we are ready to do SGD. So remember, we have a data set that looks something like this. It has around, well, it has around, for 3s and 7, it has around 12K images, but my first set was 3s and my second set was 7s, right? Then what I can do is I can pass all of these, like the first thing I can do is I can pass all the whole data set to the model and I can get some predictions. And then I can calculate the loss, then I can calculate the gradients, and then I can do this step over and over again until my loss is reduced. But it's not a good way of doing so. Why? This is dependent on the fact that my whole data set can fit on a GPU. Because remember, the model is on a GPU, right? So this is dependent on the fact that my whole data set can fit on a GPU, which would never be the case. Like you draw, like when you have ImageNet size data sets which are 1 million images, then they will never fit on a single GPU. So something you instead do is you just take a subset of this data set, which is called a batch. So let's say I just take my first 64 images. So in that case, my batch size is 64, and I pass this 64 to the model. I get the predictions, I calculate the loss, I update my parameters based on this loss, and I keep doing this over and over again. So next 64, then 64, and the last 64. And once I've done all of them, that's when it's referred to as one epoch. But I can do this over and over and over again. And that is referred to as mini batch. So this 64 is just a mini batch of the whole data set. So now let me try and show that in code. Okay. So in PyTorch, when you have a data set of 10,000 images, or basically, let's say my data set looks something like this. Let's say my data set is just 15 numbers. Okay. And what can happen is then, even if it's just 15 numbers, let's say my GPU is so small that these 15 numbers won't fit. Then I need to be able to convert this into small batches. In PyTorch, you have something called the data loader. In FastAI, you also have something called the data loader. Then what this data loader does is, see what it does? It converts those 15 into batches of 5. Because I passed my batch size as 5. That means I'm going to have 3 batches. And then because I said shuffle equal to true, then what it's going to do is it's going to randomly pick 5 elements first from 15. Then it's going to randomly pick next 5 elements. Then it's going to randomly pick next 5 elements. You could have also done this for, let's say my data set looks something like this, like 0A, 1B, then I could have again passed my data loader. I could have said my batch size is 6. Sorry, 1 sec. Then I could have again said, my batch size is 6. And in this case, then I pass in my data set and again get a data loader. So that's what a PyTorch data loader is for. It can be used to create mini batches. Okay, so that's it. So now we are ready to do, because we've defined a loss function. Now we're ready to do SGD on these 3s versus 7s. So the first thing I do is I initialize my weights randomly. The second thing I do is I can calculate my, basically I can calculate mini batches. So that mini batches is just like getting this first half of the data set. I can do the same thing for my validation images. And then I can check what my shape of the batch is. So my batch has just a batch size of 4, and each element is 784 long. Because remember, each image was 28 by 28, but we flattened it out. So that means now each image is just represented by a vector 784. So now I can pass this whole batch to my model, which we call linear 1, and we can get predictions. Finally, in SGD, then these predictions, based on these predictions, I can calculate the MNIST loss. So what MNIST loss will do is it will first convert these using sigmoid. So let me show you how that looks like. So if I say preds.sigmoid, see how it converts everything to between 0 and 1. This is 0.99, this is 0.05, and so on. So then I can calculate my MNIST loss, which gives me some value of loss. Now I can do the gradient. So loss.backward will calculate the gradients, which means it will tell me which is the direction that I need to go. And then basically now we can just put this all in a function. So don't worry about that for now. Or actually, let me just show you. So if you pass in some input, you can get the predictions, you can calculate the loss, and then you can call loss.backward. So let's see. I can calculate my gradients, and I can see that the gradient now has some value. And the basically the weights, the model weights have, the gradients have some value, and the bias of the model also has some value for the gradients. I need to zero out the gradients. I will explain this why in a second. But then the train epoch, like the this process of SGD of this whole image, which should be at the top. This image of initializing, predicting, loss, gradient, step can be converted into just this one function. So this calculate gradient takes in the inputs, takes in the actual values, and takes in a model. And it will, all this is doing is then it makes predictions, it calculates the loss, and calculates the gradient. So then I know the gradients, which means the next step for me is to take the step. So that step looks like this: p.data minus equal to p.grad slash star LR. And then I need to zero out my gradients. This should again be 0.5. So see how it gives me basically, it tells me that only my model accuracy, like it's 1/4, which means 25%. So I can calculate accuracy just by using this. So my batch accuracy, as I said, is 25%. I can calculate the accuracy for my validation set, which is 0.344. And let's say my learning rate is 1. Then let me train the model 20 times. And we can see that the accuracy has gone up from 68 to 97.4. Sorry, guys, 1 sec. Wow, I really have a bad cough. I didn't realize. I think it's all the talking that's irritating my throat a little bit. So in that case, then we get all the predictions, and you can see how my loss is going up. Okay, I think I will stop here. I did mean to cover the optimizer, but I'm not feeling the best. But I will stop here. Let me just go back and see if there's any questions. Please write the YouTube session link. We will do. What impact would it have for the training if all threes, all sevens, all first as threes and all first as sevens, or randomly shuffle them? Okay, Vinayak, that's a great question. But something I would say is, instead of asking, do an experiment and write a blog about it. So this is a great question that you've asked. Go back and see if there's any difference that you can get in accuracy. And then try and come up with a possible theory on why it could be. If you find, like, if you think deep enough and you can't come up with a reason, start a discussion group, put it on Slack, share your experiment, and then share your findings with people. And this is how you learn the most about deep learning. Like that is something I did a lot when I first started. Cool. So that's where we'll stop. I'm really sorry. I'm not feeling very well on my throat, but I will go back and we will just wrap this up. It will take us next 10 minutes to wrap this up from this point forward in our next session. But in our next session, then when you come back, we will start. With pet breeds. But for now, go back, have a look at stochastic gradient descent. Understand everything. Relate what we've learned so far to code, and then run all the code that there is. And that should be all. Thanks, guys. Thanks for today. I'm really sorry for not feeling very well.